In this section, we want to continue our discussion about aqueous reactions. And there are two other types of reactions that sometimes occur in aqueous solutions. The first is acid-base reactions, and then the next is oxidation-reduction reactions, which may or may not occur in aqueous solution. So let's look at the acid-base reactions first, which do occur in aqueous solution. So one of the first things we need to do is identify these 7 strong acids. Those are hydrochloric, hydrobromic, hydroiodic, HCl, HBr, HI, chloric, perchloric, nitric, and sulfuric. These are all strong acids. All other acids are weak acids. Now there's a couple other acids out there that may be considered strong acids, but you don't need to worry about them for this course. In the case of strong bases, we have 1A metal hydroxides and a couple of 2A metal hydroxides, calcium hydroxide, strontium hydroxide, and barium hydroxide, which are strong bases. And these compounds dissociate in solution. So an acid is a covalent compound containing H and Cl, but it acts as if it is an ionic compound because it breaks up into H plus and Cl minus. And because it's a strong acid, it completely dissociates in water. Strong bases form hydroxide ions in solution, so they're soluble metal hydroxides. So if you look at your solubility rules, calcium, strontium, and barium are exceptions. Generally, hydroxides are insoluble, but these are exceptions for hydroxides. Here's an example of a 1A metal. 1A metals are always soluble, and a hydroxide forms sodium and hydroxide ion in solution, just like any other ionic compound. This is actually what's found in Drano. So now we have an example of a strong acid and a strong base. There's one other thing that I want to show you about strong acids. When you learn about acids later, and usually in general chemistry too, you may see them interacting with water. So if we take HCl, aqueous, and we react it with water, water will actually act as a base and accept a proton, and you'll end up, this is a liquid, you'll end up with H3O plus, aqueous, plus Cl minus, aqueous. This is the same thing as HCl, aqueous, yields H plus, aqueous, plus Cl minus, aqueous. These are just two different ways of writing the same thing. In one case, it's breaking up into the component ions. In the other case, it's reacting with water. I should note that the bottom one is probably closer to what's actually going on in real life. Note that if you have a weak acid, like if you look at CH, CH3COO, which is acetic acid, aqueous, plus water, liquid, some of it will interact with water to form H3O plus, aqueous, and CH3COO minus, aqueous. This is acetic acid found in vinegar. So here we have some of it reacting to form these, that's why you have a short arrow, but most of it will stay as the acid. So a strong acid will completely react with water. A weak acid will only partially react with water. But it's a little bit different if you have a weak acid reacting with a base. So let's look at what would happen there. If you take, I'm going to switch to a new slide. If we take H, CH3COO, aqueous, acetic acid, and react it with a strong base, for example, KOH, aqueous, we now have a special type of double displacement reaction. We have H plus and acetate minus, K plus and OH minus. H goes with OH, K goes with acetate. So if we have H plus and OH minus and we cross them, this is not very necessary, we get HOH. Note that HOH is much more commonly written as H2O. And for whatever reason, it's usually written second. So we end up with water. Note that water is not aqueous, which is the driving force of this reaction. In double displacement reactions, in order for them to occur, as we saw in the previous section where we formed a solid, we need to form something that's not aqueous. In this case, we formed water that's liquid. What do we have left? Well, we have K plus and CH3COO minus. Cross them, and we get KCH3COO, aqueous. So, and this is balanced because we have one H, one of those H's, OH, the other H and the O, acetate, acetate, K, and K. So it's all 1 to 1. So this is the balanced chemical equation. Note that if this would be called a molecular equation for an acid-base reaction, and we could write this as a net ionic equation. And in a net ionic equation, what do we have? Well, what did we form that's not aqueous? We formed H2O liquid. And what ions did we need to form that? Well, we needed H plus aqueous and OH minus aqueous. So an acid, this type of acid, generates protons, H plus in water, and a base is a metal hydroxide, a 1A or a 2A metal hydroxide, which forms OH minus in solution. So this is basically the net ionic equation, and this is the molecular equation. Let's look at another example of a strong acid and a strong base. Let's say that we took H2SO4, aqueous, and we reacted it with NaOH, aqueous. Well, H goes with OH and Na goes with SO4. So when we do this reaction, H and OH form water, which is a liquid, which is the driving force of the reaction. We now have sodium interacting with sulfate. So we have Na plus SO4, 2 minus. Cross them, and you get Na2SO4, aqueous. Note that we have 2 sodiums here, so we need 2 NaOHs. If we have 2 H's, because this is H2SO4, and 2 OHs, and each H and OH forms water, so we'll have 2 waters. Note that sometimes it's better to think of this as HOH, where the H comes from the acid and the OH comes from the base, so we have 2 hydroxides. If there's 2 of these, we have 2 hydroxides and 2 H's. So if we think of water as HOH, it can be helpful. So now we have the balanced chemical equation here. What if we wanted to write the net ionic equation? Well, what are we going to form? We're going to form the thing that's not aqueous. So 2H2O liquid. Well, what do we need to do that? We need H plus aqueous plus OH minus aqueous, and in an acid-base reaction, H plus and OH minus form water, but in this case there's 2 of each. So this is the net ionic equation. An interesting question is whether you should cancel out all of those 2's, and I'm not going to get into that here. Technically, you should probably cross out all of the 2's because they're all 2. And this is the molecular equation. So this is basically what you can do for acid-base reactions. However, there's another type of base that you need to be familiar with, which is a carbonate base. And if we take HCl, aqueous, and we react it with Na2CO3, aqueous, this will also form a double displacement reaction, and this is actually an acid-base reaction, similar, or this is commonly done in our labs to neutralize acid. We use sodium carbonate or sodium bicarbonate. In this case, H goes with CO3 and Na goes with Cl. So we have H plus and CO3 2 minus. We cross them, and what we get is H2CO3. Notice that H2CO3 is the same as CO2 plus H2O. There's 2 H's, 1 C, and 1, 2, 3 O's. So this decomposes into carbon dioxide and water. So instead of getting H2CO3, we get H2O liquid plus CO2 gas. Now, what else do we give? We have Na plus and Cl minus. So Na goes with Cl, and we get NaCl aqueous. In order to make this work, we need two HCl's, and we get two NaCl's to balance. Here, we could write the net ionic equation as forming the things that are not aqueous. So this is the molecular equation. And if we wanted to write the net ionic equation, we could. Well, what is not aqueous? We have H2O liquid plus CO2 gas. And what do we need to form this? Well, we need H plus and CO3 2 minus. So we need the two H pluses, aqueous, plus CO3 2 minus, aqueous. And again, this is the net ionic equation. So here we have another example. The only difference here is that this would be called carbonic acid, is not stable at room temperature, so it quickly breaks up into much more stable molecules, carbon dioxide and water, so we have this decomposing. Notice that this does form a gas, so if you were to do this, you would actually see fizzing. So here are some examples of acid-base reactions, which are kind of just a special type of double displacement reaction. Next, we want to look at something called oxidation states, which is kind of switching gears to another topic. So oxidation states. Oxidation states are an electron bookkeeping system. And they're kind of like charges, except they're not actually charges. They're just oxidation states. And there's a few rules to keep in mind. The first is free elements have an oxidation state equal to 0. So anything that's an element has an oxidation state of 0, like sodium or chlorine. Monoatomic ions have an oxidation state equal to their charge. So sodium is +1, chloride is -1. The sum of the oxidation states is equal to the charge on the compound, often 0. So sodium is +1, chloride is -1, the total is 0. The sum of the oxidation states on polyatomic ions equals the charge on the ion. So in the case of nitrate, the total of the oxidation states is -1. That makes nitrogen +5, and each oxygen is -2. Group 1A metals have +1 oxidation state in their compounds. 2A metals have +2 in their compounds. And non-metals have oxidation states according to the table on the right. Fluorine is always -1, hydrogen is always +1, oxygen is always -2. Then these come into play sometimes, but usually things are with oxygen, okay, especially in the polyatomic ions. So oxygen has an oxidation state of -2. Remember that oxidation states are different than charges. In covalent compounds, chemicals have oxidation states. Why oxidation states are important and why electron bookkeeping is important is because if electrons are transferred, the elements or the compounds can be used in electrochemical applications, so they can make batteries work, which is of course important to our cell phones and whatnot. So let's take a look at finding the oxidation state, which is very similar to finding the charge in ionic compounds in several examples. So let's first look at the example of water. Let's find the oxidation states in water. Notice that oxidation states are not charges. This is an electron bookkeeping system. So what I do is I always remember that oxygen has an oxidation state of -2. The only time this isn't the case is if it's with fluorine, and I won't give you one where it's with fluorine, so you don't have to worry about that. So the oxidation state of oxygen is -2. I should mention there may be other cases, but the common case is where it's with fluorine. So here, how are we going to find the oxidation state on hydrogen? Well, we could look at the previous chart and see that it's +1. Or we could do 2 times hydrogen -2, the oxidation state on oxygen, equals 0. 2 hydrogen minus 2 equals 0, +2, +2. 2 hydrogen equals +2, hydrogen equals +1. So now we know that this is +1 and this is -2. Those are their oxidation states. Let's look at another example. Let's look at sulfur in SO4 2 minus. They are called oxidation states, so let's learn the oxidation state of oxygen and remember that it's -2 unless it's an element. In O2 it's 0. The oxidation state of all elements is 0. So let's find the oxidation state of sulfur in this. So we have sulfur plus 4 times -2. There are 4 oxygens, each with a -2 oxidation state, equals -2, the overall charge on the polyatomic ion. Sulfur -8 equals -2, plus 8, plus 8. Sulfur equals +6. So that is the oxidation state on sulfur. And in a few minutes, you'll see where this comes into play if we're looking at reactions that are occurring, which are oxidation type and reduction type reactions, which again can be used to power batteries or power cell phones with batteries, for example. Let's look at another example. Let's look at phosphorus in phosphate, PO4 3 minus. Well, we do it the same way as before. Phosphorus plus 4 times -2. 4 oxygens, each with a -2 oxidation state, equals -3. Phosphorus -8 equals -3, plus 8, plus 8. Phosphorus equals +5. So this is how we find the oxidation state. The oxidation state on phosphorus plus 4 times the oxidation state on oxygen, which we have to know is -2, equals the overall charge, which is -3. Let's do a couple more examples of finding oxidation states. Let's look at an example of CO and CO2. And in both cases, we want to find the oxidation state on carbon. So these are not polyatomic ions, these are neutral. Also, these are not charges, they're oxidation states, because here, this is not an ionic compound, so the species do not have charges. So if we look here, it's carbon -2 equals 0, +2 plus 2, carbon equals +2. So it's the oxidation state on carbon plus the oxidation state on oxygen equals the overall charge. These are neutral, so it's 0. Here we have carbon plus 2 times -2, 2 oxygens, each with an oxidation state of -2, equals 0. Carbon -4 equals 0. Carbon equals +4. So this is an example where, in this case, carbon's oxidation state is +2. In the carbon dioxide case, it is +4. So they are not both the same, even though they're both carbon and oxygen containing compounds. So this is finding oxidation states, which is important because it leads us to the next step, which is using oxidation states in chemical reactions. So in chemical reactions, we want to understand what is oxidized and what is reduced. So oxidation means electrons are lost. Reduction means electrons are gained. If electrons are lost, something's charge goes up. If electrons are gained, something's charge goes down. Oxidizing agent is the reactant that was reduced, and reducing agent is the reactant that was oxidized. And there's 2 mnemonic devices. This is probably the more common one. Leo the lion says grr. Leo means losing electrons is oxidation, and grr means gaining electrons is reduction. So what I want to do now is look at a series of reactions and determine, first of all, if oxidation and reduction have occurred, and then finally, what is oxidized, what is reduced, what is the oxidizing agent, and what is the reducing agent. So let's look at this example. If we have 2 magnesium solid plus oxygen gas yields 2 magnesium oxide solid, we want to know if this is an oxidation reduction type of reaction. So in order to determine whether this is oxidation or reduction, we first need to look at oxidation states. Well, we can automatically tell that this is oxidation or reduction because we have elements forming a compound. In elements, oxidation states are 0. In compounds, they're not. So we know they've changed. If they changed, it's an oxidation-reduction reaction or a redox reaction. So here, the oxidation state on magnesium is 0. Here, the oxidation state on oxygen is 0, again because they're elements. We need to remember that elements have an oxidation state of 0. Now we need to find the oxidation states over here. Well, since this is a simple binary ionic compound, the oxidation states are equal to the charge. Magnesium is +2, oxygen, which we just did several examples, has an oxidation state of -2. So magnesium has gone from 0 to +2, and oxygen has gone from 0 to -2. So let's remember our Leo the lion says grr. Losing electrons is oxidation, gaining electrons is reduction. So magnesium went from an oxidation state of 0 to an oxidation state of +2. It lost electrons. It has undergone oxidation. If magnesium has undergone oxidation, oxygen should have been undergone reduction because those lost electrons had to go somewhere. Well, where'd they go? They went to oxygen. Gaining electrons is reduction. It went from 0 to -2. It gained 2 electrons. So this is reduction. Now, if oxidation occurs to magnesium, it is the so-called reducing agent. And if reduction occurs to oxygen, it is the so-called oxidation agent. Remember, the agents are opposite. The thing that undergoes oxidation is the reducing agent. The thing that undergoes reduction is the oxidizing agent. So they are opposite of each other. Oxygen, except for with fluorine and maybe some other cases, is almost always the oxidizing agent. All right, that's where oxidizing comes from. Let's look at another example. Let's say we have 4 carbon monoxide, CO, gas, plus 3 O2 gas yields 4 CO2 gas. So here we have a reaction. In this case, we do have an element, but we also have a compound. So we need to look at the oxidation states here and see what's going on. Well, here, oxygen has an oxidation state of 0 because it's an element, and here, oxygen has an oxidation state of -2 because it's in a compound. Now, if you'll recall from the previous example, we actually found the oxidation state of carbon and carbon monoxide and carbon dioxide. So here in carbon monoxide, it's +2, and here in carbon dioxide, it's +4. You could figure that out again, just exactly the same way that we did here, where we have carbon and carbon monoxide and carbon dioxide. But here I'm just going to put them. So carbon goes from +2 to +4. Let's look at what's going on. If something goes from a charge of +2 to +4, did it gain electrons or did it lose electrons? Well, its charge went up, so it lost electrons. Losing electrons is oxidation. And therefore carbon monoxide is the reducing agent. In the case of oxygen, it went from 0 to -2. It gained electrons. Gaining electrons is reduction. So therefore, this is reduction. And oxygen is the oxidizing agent. Note that this oxygen is -2 on both sides. It's -2 here and -2 here. It was not oxidized nor reduced. This O2 underwent reduction and is the oxidizing agent. It is not the oxygen of carbon monoxide in this case. Let's look at one more example. Let's look at copper NO3 2. Copper 2 nitrate, aqueous, plus zinc solid yields zinc NO3 2 aqueous plus copper metal. So we can find the oxidation states of zinc 0 and copper 0. But what about in these compounds? Well, here we have copper, and we want to find its oxidation state. said another way, we want to find its charge because it's an ionic compound. We know that because it contains a metal, plus 2 times minus 1, 2 nitrates, each with a minus 1 charge, equals 0. Copper minus 2 equals 0. Copper equals plus 2. So copper is plus 2. Whoops, I meant to write that down here. Now let's look at zinc in zinc nitrate. We have zinc minus or plus 2 times minus 1 equals 0. It still has 2 nitrates, each with a minus 1 charge. Zinc equals plus 2, just like copper, plus 2. So copper went from plus 2 to 0. In order for its charge to go down, it was positive 2 and now it's 0, it had to gain electrons. Gaining electrons is reduction. So this is reduction. And copper nitrate, or copper 2 plus, is the oxidizing agent. In the case of zinc, it went from 0 to plus 2. It lost electrons. This is oxidation. And zinc is the reducing agent. So these are examples of oxidation reduction reactions, which this electron bookkeeping allows us to do. And here in this case, we actually formed copper metal from a copper salt. That can be practically useful. So these reactions are very practically useful. The last thing I want to talk about is 2 more types of chemical reactions. So we already talked about a combination, decomposition, a combustion, and now we've looked at 2 more, which are a single replacement, which we just did with the copper nitrate and the zinc. That is A plus BC yields AC plus B. And this is called a single replacement or displacement reaction. So A replaces B, and now it's with C. Here's an example. If we take copper sulfate, aqueous, and we react magnesium, metal, magnesium can go with sulfate, MgSO4, aqueous, and leave copper, metal. So magnesium replaces sulfate. This is an oxidation reduction reaction, just like the one we just showed, but it's also a single displacement reaction. The other one you've seen already is the double displacement. Here we have 2 replacements occurring. This is AB plus CD. A goes with D, C goes with B. So we get AD plus CB. And this is a double displacement reaction. And one example of this, where we form something that's not aqueous, if we take magnesium nitrate, aqueous, and we react it with 2 sodium hydroxides, aqueous, we can form magnesium hydroxide. And hydroxides are generally insoluble, so that's solid, plus 2 sodium nitrates. And sodium compounds and nitrate compounds are generally aqueous. They're soluble in water. So this is a double displacement reaction. And in it, we've seen examples of both of these throughout this section. In order to remind you of all the types of chemical reactions that you're responsible for, we have the combination, the decomposition, the combustion, the single displacement, and the double displacement, all on a single slide here for the types of chemical reactions. In part 1 of this slide earlier, we just had the first 3 because we hadn't gotten to the second 2 yet.